Welcome to your AP Statistics, Chapter 14, Introduction to Probability lesson. This is Mrs. Brown, and I'm here today with both my dogs, Daisy and Scout, and we are ready to talk probability. Okay, so let's just kind of review in statistics what we mean by a random phenomenon. It's a situation in which we know what outcomes could happen, but we don't know which particular outcome did or will happen, and there's typically a pattern to the occurrence. In general, each occasion upon which we observe a random phenomenon is called a trial. At each trial, we note the value of the random phenomenon and call it an outcome. So each trial has an outcome. When we combine outcomes, the resulting combination is called an event, and the collection of all possible outcomes is called the sample space. When thinking about what happens with combinations of outcomes, things are simplified if the individual trials are independent. Roughly speaking, this means that the outcome of one trial doesn't influence or change the outcome of another. The one outcome occurring does not change the probability that the other outcome will occur. For example, coin flips are independent. The law of large numbers is an important concept. It says that the long run relative frequency of repeated independent events gets closer and closer to a single value, which is the probability of the event. Because this definition is based on repeatedly observing an event's outcome, this definition of probability is often called empirical probability. Now, many people misapply the law of large numbers and think that it's going to happen in the short run, and you'll hear people refer to the law of averages. So, relative frequencies even out only in the long run. This means that the long run is really, really long. Um, so, the so called law of averages, that an outcome of a random event that hasn't occurred a good number of trials is due to occur, doesn't exist at all. All right, so there's empirical probability, and that's great. And we can talk about probabilities in the context of contingency tables, and that's a great way to work with empirical probability. But there's also theoretical probability, and we can thank French mathematicians who were sponsored by people who were interested in gambling for formalizing the study of probability. They started off with games in which all possible outcomes were equally likely. For instance, anything involving rolling a single fair six-sided you are equally likely to get any of the one of six outcomes: 1, 2, 3, 4, 5, 6. Is also equally likely to get heads or tails from the toss of a fair coin. So that was another game they looked at. However, keep in mind that events are not always equally likely. A skilled basketball player has a better than 50-50 chance of making a free throw. The probability of an event is the number of outcomes in the event divided by the total number of possible outcomes. Now, another type of personality, another type of probability that we're not really going to look at much is personal probability, and it's just a subjective probability. Oh, there's a 70% chance I'm going to take a nap this Sunday afternoon. Well, that doesn't display any kind of consistency. And it's not really based on anything other than what I'm feeling right now at the moment. So we're not really going to study that, but you need to know that that is a type of probability also. Okay, when working with empirical or theoretical probabilities, the ones we're talking about, it's sometimes good to start with a picture. The most common kind of picture to make is called a Venn diagram, and we'll see them in practice in just a minute. Right here, as we are talking about the different rules of probability. All right, there are two requirements for a probability. Okay, so the description of the likelihood of an outcome. A probability is a number between 0 and 1. Events that cannot happen have a probability of 0, and events that must happen have a probability of 1. So for any event A, 0 is less than or equal to, and that stands for probability of A, less than or equal to 1. All right. Another important rule is the probability assignment rule. The probability of the set of all possible outcomes of a trial must be 1. Something has to happen. Okay, S is the sample space. You can see here's a little diagram. S is everything that can possibly happen. The probability that something happens is 1. If we have a way of defining one event as A, and so the sample space is divided into A and not A, we call not A the complement of A. And the two together must add up, the probability of the two together must add up to be 1 because they make up our entire sample space. So it follows that the probability of A is 1 minus the probability of its complement. Okay, when two events have no outcomes in common, we know these two, A and B, have no outcomes in common because in this Venn diagram, they don't overlap. We call the two events either disjoint or mutually exclusive. There's no overlap. So for these two probabilities, we can find the probability that A happens or B happens simply by adding together the probability of A plus the probability of B. What happens if there is an overlap? We're going to talk about that next time, but for today, we're just going to use the addition rule when we have disjoint events. Okay, we mentioned independence earlier. That means knowing that one event occurs does not change the probability that the other event occurs. All right, so if we have independent events, remember this is not the same thing as disjoint or mutually exclusive. Mutually exclusive events, if I know A occurs, that brings my probability of B occurring down to 0. So they can't be independent. Okay, so with independent events, a really cool phenomenon is that the probability of A and B occurring is the probability of A times the probability of B. Many statistics methods require an independence assumption, but assuming independence doesn't make it true. Always think about whether that assumption is reasonable before using the multiplication rule. It's really handy when we are told in a prompt that the two events are independent, but sometimes that does not happen. It's most likely that you're going to be using these rules of probability in combination. A good thing to kind of keep in mind is sometimes it's easier to work with the complement of an event that we're interested in and then subtract that from 1 and we'll get the probability of the event of interest. Okay, be careful of probabilities that don't add up to 1. To be a legitimate probability distribution, the sum of the probabilities for all possible outcomes must total 1. Okay, if you're looking at all possible outcomes, that represents 100% of what can happen, and that 100% of what can happen is analogous to a probability of 1. Don't add probabilities of events if they're not disjoint. We'll learn how to correct for overlap next time. And don't multiply probabilities of events if they're not independent. We'll talk about how to find analogous probabilities next time for events that are not independent. Don't confuse disjoint and independent. Remember, disjoint events can't be independent. All right, so look over the problem in on page 339, exercise number 20. From that, we get that the probability of no calculus is 0.55, and the probability of one semester of calculus is 0.32. Okay, the only other possible outcome would be probability of 2 or more semesters. So combined, no calculus and 1 semester provide us the complement of 2 plus semesters. So we add those together and subtract from 1, and we get 0.13. All right, probability of some calculus. Well, there's a couple of ways we can do that. Um, we can go with, oh, okay, some calculus means 1 semester or 2 or more semesters. So that's going to be 0.32 plus 0.13, which is 0.45. Alternatively, we could have done, oh, probability of some calculus is equal to 1 minus the probability of no calculus, and then 1 minus 0.55, but that would give us the same thing. The probability of no calculus of 1 semester, we can just add up the 0.55 and the 0.32 to get 0.87. And again, we could have gone, oh, that's the complement of 2 or more semesters, and done 1 minus 0.13, and we would have had the same result. Assuming independence, we can find the probability of neither studied calculus of the 2 individuals, and so that's going to be 0.55 times 0.55, which is 0.3025. Both have at least 1 semester of calculus, so that's going to be the probability of some calculus times the probability of some calculus. And so 0.45 times 0.45 is 0.2025. One thing I want to point out, notice I show work. I don't just boom throw down an answer. At the AP reading, we call those naked answers because they're not clothed in any calculation or any meaningful description. You want to show what the probability of what you're interested in, and then you want to show what you're adding together, what you're multiplying, and then you want to show the answer. For a couple of reasons. One, it's required to get full credit, and 2, if you accidentally typed in 0.55 times 0.5 and got the wrong number for your answer, you would get absolutely no credit for that. And if you had done that, but you had the correct numbers multiplying together, you would get full credit. They understand that sometimes there's just calculator errors. It is in the description of what you're looking for, and in the plugging in of the numbers, okay, showing the work that demonstrates you understand what's going on. Okay, so the probability probability at least one had 2 or more semesters of calculus is 1 minus the probability that neither had 2 or more semesters of calculus, right? So at least one. So you can have the following situations. Neither had 2 or more semesters of calculus, one had 2 or more semesters of calculus, or both had 2 or more semesters of calculus. So the easiest thing to do is to figure out the probability that neither one had 2 or more semesters of calculus, and then subtract that from 1. So it's going to be 1 minus 0.87 times 0.87, and so you get 0.2431. Okay, exercise 24 on page 339. We're assuming that that the calculus background of each group member is independent. Yes, the professor assigns students to group randomly, making independence a reasonable assumption. So if students got to pick their groups, it could be that the students who are high achieving study together, and so they would opt to work together, and the students who were kind of slackers and show up late and sit in the back of the room might end up all together, choose to be in the same group, or be chosen by the rest of the class to be in the same group, because all groups are formed before they're invited, so by default they have to be together. If students chose the groups themselves, it would not be random. And so you wouldn't have independence. If the professor assigned the students to groups based on their work habits, again, independence wouldn't be reasonable. If there's anything systematic in the way the professor or the students form the groups, then independence is not a reasonable assumption. But because the professor did use randomization, independence is reasonable. Okay, guys, that's it. do the problems to try on your own. I look forward to working with you on probability in next class. I will tell you that we're going to look at more complicated kind of situations in chapter 15. So it's really important that you get the chapter 14 concepts down um, before we move on to chapter 15. All right, guys, have a good day. If you need me, email me or swing by my class.